All right, folks. So today we're going to talk about page 10 of the ESRT. This is the inside of the Earth diagram, and there is a ton going on. So to start off, we will have our four main layers of the Earth. We are going to have the crust. So the crust is, I highlighted on the left-hand side here for you where the label is. The crust is the very outside shell of the Earth. It is going to be our thinnest section on this diagram. Our second layer is going to be the mantle. Now, the mantle is going to be comprised in this diagram as two layers: the asthenosphere, otherwise known as the plastic mantle, and then the stiffer mantle, the much thicker layer right beneath the asthenosphere. We also have our outer core right here, and that is going to be the liquid layer of the Earth. I'm going to talk about why or how we know this is considered to be liquid later on in the PowerPoint. And we also have our solid inner core down in the bottom right hand corner of this diagram. So this diagram is if you took the Earth, cut it in half, and then cut it in another half. So we're looking at like a quarter of the Earth, a cross section of it, a look of the inside. The second really important thing on this diagram are these dotted lines. So these dotted lines on the left-hand side, I'm going to cover them in thick black lines. These are what connect the chart to the bottom portions of the diagram. So these dotted lines separate the layers of the Earth. So if you come straight down the diagram from the mantle, you're going to stay in the mantle if you stay within those two dotted lines. Okay, so I'm going to address some of the newer words on this diagram. We have this thing called the lithosphere. So the lithosphere, it's the very upper portion of the mantle and the crust. So this upper portion of the mantle is much stronger than the asthenosphere, which I'll talk about momentarily. It's a very hard rock, and it is going to be grouped in here with the crust, the hard rock that we live on. So this diagram does have lithosphere diagram for you, and it is right next to where it says crust and rigid mantle. So if you're ever encountered with a question, what two pieces of the Earth are in the lithosphere, you can come here and see that it's paired with the crust and rigid mantle. Not something you're going to need to memorize. Okay, next important word is our asthenosphere. So the asthenosphere is the portion of the mantle directly below the lithosphere. And what's really important about the asthenosphere is that it has the ability to flow. There are convection currents within the asthenosphere. And these convection currents, the rising of hot material and the falling of that material as it gets colder. It's just like with warm air. As warm air rises, it is it eventually will start to cool down and sink. So it's a constant circular motion of hot materials, in this case, hot rock. So we have two convection currents labeled on this diagram. We have one at the top where it says Mid-Atlantic Ridge right above, and we'll talk about that term momentarily in the unit. And then we also have one in the bottom left that says this word trench, another thing we'll get to as the unit goes on. So what's really important here is that as the mantle has these convection currents in it, we have the lithosphere sitting right above it, the crust that we live on. So when the rock underneath of us is moving, what's going to happen is the crust is going to get pulled along with it. Now, I'm not going to play this video right now. I'll show it to you guys in class. So I want you to think about the treadmill being the asthenosphere, the convection currents underneath the crust, and the child being the crust or the lithosphere. So what happens is this child, well, you guys can see right here. So I know that's pretty funny, but it's an accurate description here. The asthenosphere, the treadmill, is spinning in a circle like a convection current, and the crust on top gets pulled along with it, just like this child. So here's an image of what you could see to represent the convection currents. So first thing I want to point out is that we have warm, hot material rising in the mantle. Now, it can only rise so much because eventually it's going to encounter the crust. So when it does encounter the crust, it starts to spread out. So we have the rising, spreading out of the hot material in the mantle. This is going to, just like the treadmill in the child, take the crust along with it. So we have the moving asthenosphere pulling the lithosphere with it. Now, it's going to continue to move. So it continues to move and it continues to pull the crust. And eventually, that hot material is going to cool and go a part of the convection cycle where it sinks back down to the core of the Earth. Now, it's going to pull the lithosphere underneath the crust. So this is where that word trench is coming into play. We are pulling crust down into the interior of the Earth. So as the mantle continues to go through that convection cycle, that spinning of hot and cold material, it eventually works its way back to where it starts to rise and repeats this cycle all over again. Okay, so far we've talked about the crust and the asthenosphere. So we've talked about the lithosphere and the asthenosphere. We're going to still dive a little deeper and talk about the stiffer mantle. So it is similar to the asthenosphere. However, it's much more dense. So it doesn't move like the asthenosphere does. Here is it labeled in your diagram. It is with the dots surrounding the stiffer mantle in the label. Now, when I talk about the stiffer mantle being denser, we can see this on the diagram. So on the very right-hand side, for each layer, there is a range listed of the densities for the material that's in that layer of the Earth. As you get deeper into the Earth, the density of the rock is going to increase. So if you look at the very top right-hand corner, it'll say density at the top, and then it'll give us the densities for what we call continental crust and oceanic crust. Now, we have a 2.7 grams per cubic centimeter for our continental crust and a 3.0 grams per cubic centimeter for our oceanic crust. This is meaning that the ocean crust, the crust that sits below the ocean, is a bit denser than the crust we are currently walking on here in Fairport on the continent of North America. Now, as we move a little deeper into the stiffer mantle, our density range is increasing from 3.4 to 5.6, still increasing into the outer core and still increasing into the inner core. So we don't have to memorize any of these densities. We just have to be able to look at this diagram and be able to determine which layer is going to have a higher density. Okay, we're going to continue our journey to the center of the Earth. This time we're going to stop at the core. And there's going to be two layers of the core. We are going to have the outer core. This is liquid rock. Liquid rock. And we know this because of earthquakes and the S waves' inability to travel through the liquid outer core. And we also have our inner core. This is solid, extremely, extremely dense iron and nickel. So this chart, it continues downward on the page, and it continues to talk about pressure. And what we can see on this diagram is that pressure increases as our depth increases. Now, depth is labeled all the way at the bottom of this diagram. And here's our pressure, this entire chart right there. And depth is going to increase as we move to the right. So what the pressure line is doing, that black line going across this diagram, is increasing as the depth or how far we are into the Earth is also increasing, a direct relationship. Now, remember those dotted black lines that I talked about in the beginning of the video? They come back into play here because we have different zones in this pressure diagram. All the way on the left in the green, we have this little thin sliver for the crust. Then we have this box for the stiffer mantle, the outer core, and the inner core. So, hypothetically, you could be asked, what is the density or the pressure, at a certain kilometer distance inside the Earth. You can use the depth measurement at the bottom of this chart, go all the way up until you hit this line, and you can read the pressure on the left-hand side here. It's 0 through 4 million of atmospheres of pressure. We also have a temperature chart on here. And the temperature chart is a couple things. It is showing us that temperature increases as our depth increases, just like pressure. So when we're looking at this temperature chart, there's going to be a solid line that is the interior temperature, the temperature that it is at a certain depth. There's also the dotted black line, which is the melting point. This is the temperature that a rock has to reach in order for it to melt and become liquid. So just like the pressure diagram, we are increasing as depth increases. And we have our different segments. We have the crust on the left, the mantle, the inner core, or I'm sorry, that's the outer core, and the inner core. Now, how can we tell the outer core is liquid? A really cool bit of information on this diagram. Now, we can tell that the outer core is liquid by noticing that the temperature is higher than the melting point in this portion of the chart. So if we look at the outer core area between its dotted lines, we can see that the black temperature line is above our melting point, telling us that these rocks have heated up enough to turn them into liquid. So what I hope you can take away from this presentation is that we have this picture of what the inside of the Earth looks like. And then we have two other charts, our pressure and temperature, that we can use in combination together to determine certain characteristics of the inside of the Earth. So please let me know if you have any questions. I hope you found this helpful and have a wonderful rest of your day.